we created a file compression program using Haskell, and we used many functional programming concepts and compression concepts in this program. So it is written in Haskell. There's a main file and multiple modules for handling I/O for the data types and to do the actual processing, and there's a util file for counting frequencies of the characters. Here we use Kbal for as a package manager. So to build this, we do a build. So let's see if the compression works. So we have a lorem ipsum here, about 227 lines text file, and we will use this command, and parallelization is enabled, and we give a C for compression flag. And if we do, let's call it .half, and we do the command, and you can see file is generated. So this is in binary, and if we do a you can see the actual text file is 66 kilobytes and compressed file is about 38 kilobytes. So file is compressed to half of its size, about half. And if we do the decompression, check, we give the D flag and we decompress .half back into lorem decompress.txt. So decompression is completed, and we can see the size is same again. Let's see, the information is there. So you can see it's the same, and it has 227 lines. It's the same file. So if we analyze this file using this hex editor, so this is how it works. So this first byte says how many characters are in the file. So this is the file header, and here there are 42, so it means 42 characters are in this file. So one by one it says the character is 4 times. So it counts frequency for each character in the file, and we store this all. So after the file header is there, and the rest of it is just data. So it uses Huffman Coding for compression. So Huffman Coding is a lossless data compression algorithm. So let's say we have this text ABCCC, and if we store this in computer in ASCII, each character takes like 1 byte, so there will be like 5 bytes. Instead we can create a Huffman tree from this. So this is that tree. So A appears 1 time, B appears 1 time, C appears 3 times, and 3, 5, like that. And this is a binary tree, so this side is 0, this side is 1, and we convert this into the Huffman Coding. We get A is 0, say is here, so it is 0 0, and B is 0 1, and each C is 1. So it only takes like 1 byte to store this entire information. This is the original Huffman algorithm, but if we use this, we have to ship this entire tree with the file, so the code book. So it reduces the efficiency. So instead we use this canonical variant, which we used in this program. So and here we used canonical Huffman coding. So we take the bit length of this original encoding. Bit length is 2, B is 2, and C is 1. So C has the lowest bit length, and A and B have 2 bit length. So we sorted this, so sorted by alphabetical order, C, A, B, and C is 1 bit, So the first one always gets 0, and A always get A has 2 bit length, 0 0, and then we add 1, but we left shift this bit, so it is this. And because we changed the bit length from 1 to 2, and then from A to B, same bit length, but we add 1, so it's 1 1. So C has 1 bit length, it is 0, and when it comes to A, we change the bit length, so when we add 1, we have to left shift the bit, and this is same bit length, so we add 1. This is the new coding, so it is different from the original coding, and this is what we used in our application. So now if we go to this main.html file, when we do a compression, this is where it goes, and here this is the workflow. So we first read the content of the file, and we do the counting of the character frequencies, and we get that, and we create the original Huffman tree, and from that, as I said before, we get the bit lengths, and then we create the new canonical codes, and then we do this encoding of the file, and we write it as a binary. So if you see these encoded files, they are in a binary format. If we store the compressed file in ASCII format, it will take more bytes. Instead, we use 0 and 1 bits to represent this compressed file, so it is in the binary format. So we write it in binary and save it. Now if we go to this frequency counting, it is in this utils file. So to frequency counting, we use this parallel library to do the parallel frequency counting. So as you can see, we use this library methods. As you can see, if the length of the file is less than 10,000, we normally count the file without any parallelization, but if it is too big, we chunk it to 4 equal sizes and use 4 cores to count each chunk. So we count the frequency counting parallelly, so this is good optimization for large files. If you go to the data types, you can see we use algebraic data types, and as you can see, this Huffman tree is a recursive data type. So Huffman tree consists of leaf or a node, and it goes on and on as a tree. So all the processing happens in this processing file. We first build the tree. You can see when we do the canonical codes, we do this left shifting and do that. This logic is in here, and this is the encoder. In this encoder, let's say, so in encoding, let's say we have A is represented by 001, but we can save it as, we can't save it like this in the as a file. We have to at least have 1 byte. So we have to fill this with less of the data. So in the encode logic, what we do is we go by character, and we take a container and A. If it is B, we store this, and then the B file comes and it is maybe 1 0 0 like that, and next one C may be 1 1 1. So we do 1 1 and byte is full. So we complete the bucket and we take another bucket and fill the rest of it is in here. So that is the encoder logic. So that logic is in here. So in a decoder, we first build the tree from the codes, and after that we go each character by character. And as you can see, this decode one has a helper function called go, and it is using a recursion. Last bit, if the compression ends, we have to fill the rest of the bucket with 0. So this is padding. We do the padding, and this is the, and we also add a variable to find what is the padding also for the last byte, and this is for if we at a padding we stop at here. So this is that logic, and if it is not padding we go to the next byte, and we go byte by byte, and if it is like a, so if it is an odd, we go left, and if we go right, like that the logic is here. So in here, when we travel bit by bit, if it is 0 we go to the left side, and if it is 1 we go to the right side. So traversing tree logic is here, and this is when we find a character, and we find a character, we append it, and we keep going until we end the whole file. So that is decoding. And if we go to the zero handler function, that is where we save the file as binary. So this binary thing, so saving this data as binary is called bit packing. So bit packing logic is here. So this is how we create the file header. First we have a number of entries. So how many characters are found, and this is the table. So for each character, how many, what is the bit length in canonical, and this is the, and this is the padding. So if there is a padding, how many valid bits are in this padding, and from this we can derive the padding, and this is the actual body, and we get that final data, and using a byte string library we write this file as binary, and reading the binary is also here. After we read the binary, we pass the table and pass the header from the binary file. That is the logic for that. So we go to this, so if we go to this processing file, as you can see in this canonical codes, it transforms frequency table into code assignment without modifying the external state. So we use immutability to make our logic predictable, and it is written in pure functions. And if you go to the decode function, you can see we used recursion. So instead of loops we use recursion, and we also use higher order functions like map, fold DL, and sort by.